I've written up some references here. So far we've been ignoring any boundaries there might be, assuming that our manifolds don't have boundaries. But obviously that's not always the case. And Hartle and Sorkin derived the Regicalculus equivalent of the Gibbons-Hawking boundary term. And I'll just tell you roughly how they did it. In deriving the Reggie field equations, you'll remember we use a particular identity that's satisfied in each simplex, which was that the sum over the hinges in a simplex of the volumes of the hinges times the variation of the dihedral angles. So the sum of the, in 4 dimensions, it would be sum of the areas times the variation of the dihedral angles within a 4 simplex of 0. Now, if you have a manifold with boundary, it may be that you don't have all the terms that you need to satisfy this identity in simplices near the boundary. So the way that Hartle and Sorkin found the extra term was to insist that they inserted exactly what you needed, so that you got the usual Reggie equations for all the interior edges, and then the assumption was that the edges on the boundary were actually kept fixed. So I probably should have written there may be a problem. So the Reggie equations hold.
Shut up.
So this extra term, you take the sum over the hinges on the boundary, you still have the volume of each hinge, and then instead of the deficit angle, another angle. This is very similar to a deficit angle, but it's defined to be, rather than 2 pi minus the sum of the angles, it's actually pi minus the sum of the dihedral angles of the hinge. And Hartle was able to show that this is equivalent to which just involves the integral of the trace of the intrinsic curvature times the square root of the determinant of the 3 metric on the boundary. So we're talking about 4 dimensions here. Now in quantum applications, it's not always the metric that's specified on the boundary. It may be the connection or some connection on the metric. And